On the last video, we found the rate law for this example equation, and now they want us to find the rate constant. The rate constant is constant for a reaction as long as the temperature doesn't change. So if you have multiple trials of the same reaction, you should get the same rate constant. So to solve for the rate constant, you can pick any trial you would like, and you're going to use your rate law, which says rate equals K NO squared H2. We figured out this earlier. And you just simply rearrange it to solve for K. So that means dividing by your reactants and their orders. So we have K equals the rate divided by NO squared and H2 to the first. And all you have to do is use the data from any experiment and plug it in. So we have our rate with its unit. Units are so key on K. Right? They almost always give you a point just if you can figure out the units. So include your units when you're calculating K. There's our rate unit, molarity per second. And then we have our concentration, which here is molarity squared, and then molarity to the first. So down here on the bottom, we have molarity cubed as our overall unit. Molarity squared, molarity to the first. So we're going to calculate the value of the rate constant just by dividing that by whatever we get on the bottom. And it turns out to be 7.5. And then if we look at our units, we have molarity on the top and then molarity cubed on the bottom. So one of those will cancel. So we'll have molarity squared on the bottom. And then seconds is also under the fraction. So that's 1 over molarity squared times seconds. Or molarity to the -2, seconds to the -1. That's just telling us they're on the bottom of the fraction. If you'll remember, we made a chart about the units for K earlier. And we said that this was the unit, or that, whichever way you want to write it, if it was third order. And it is third order, right? Second order for NO, first order for H2. So that's third order overall. So those are your units. It is essential that if we're talking about lowercase k, this is different from capital K, right? Our equilibrium constant, it has no units. But if we're talking about lowercase k, our equilibrium, or excuse me, our rate constant, lowercase k rate constant for a reaction, the units are essential because the units help us know what order it is. Right? And the last thing they wanted us to do, I think we got it all actually. Let's go back to the question. They wanted us to find the rate law, the rate constant, and then the overall order. So that was easy. We had second order for NO, first order for H2. So we know it's third order overall. All right? The next thing we want to talk about is something called spectroscopy. And spectroscopy is a lab technique. Okay? It's a method of analysis based on absorption. And it is absorption of what is known as electromagnetic radiation. So that includes infrared light, ultraviolet light, visible light, microwaves. It could be any type of electromagnetic radiation. Spectroscopy. What happens in spectroscopy is we take light that has some intensity, okay, and we know the intensity of that beginning light, and we shine it through a sample so that it strikes that sample. That sample is going to absorb some amount of that light, and the rest is going to be transmitted. So this T here stands for transmitted, and the O is for our initial, okay, or our beginning intensity. So we have an intensity of light that we shine on a sample. The sample may absorb some or a lot or none of it, and then we see how much light is transmitted. The amount absorbed and transmitted should be equal to, in total, the amount that we started with, because we can't lose or gain energy, right? So some of it's absorbed or none or all, and then some is transmitted. And the amount transmitted plus the amount absorbed equals the initial intensity. So what we can do is we can know the intensity that we started with. We can measure the intensity that comes through, so we can measure these two, and we would subtract them to find how much was absorbed. The amount absorbed by the sample is directly related to the concentration of the sample. So think about if you have really concentrated Kool-Aid, for example. It's going to be a really dark red, right? And then if you have not concentrated Kool-Aid, it's going to be a lighter red. So the concentration is directly related to the color, which is directly related to the amount of light it's absorbing. Dark red is dark red because it's absorbing a lot of light. Light red is light red because it's letting a lot of light through, or absorbing a little bit. So Beer's law tells us that the absorbance and the concentration of a sample are directly related. As the concentration of a sample goes up, so does its absorbance of electromagnetic radiation. And if the concentration goes down, the absorbance does likewise. These other two things are properties of the sample, and they are constants. So a sample has a particular molar absorptivity value, and that is related to the sample. So Kool-Aid has a specific little a molar absorptivity value. You wouldn't memorize it, you just like look it up in a table or know what it was. Gatorade has a specific molar absorptivity value. Gold has a specific molar absorptivity value. So you can actually use that to figure out what your sample is, even if you can find little a. And then B is just the path length of your sample in question. So if you're shining light through a sample that is this long compared to a sample that is this long, the short one's obviously going to absorb less light, right, than if you shine the light all the way through this long sample. So what we do is whenever we have a sample and we're doing this experiment, we always use a container that is 1 centimeter long. And it makes our math so much easier. Okay, but it could be a longer or shorter container. But that's just what we choose to use in terms of our sample length. Right, so that's Beer's law. And Beer's law is related, again, to the absorptivity of a sample. We're going to say it's going to absorb more if its concentration is higher, absorb less if its concentration is lower. So this is useful. The reason they insert this information right here is it is useful if we have an experiment that either uses or creates a colored reactant or product. So if it has a colored reactant that it's using or a colored product that it's making, that's an easy way to follow the reaction and figure out how fast it's going. We can figure out, oh, it's making a product, this much product per second, or it's using this much reactant per second. So that's why they throw that in there. So now they're telling us that they have 3 experiments that they're conducting at 25 degrees Celsius, so it's important that our temperature stays the same. And they're doing the reactions in a 1 centimeter cuvette. Okay, so that would be our B value. And what they're doing is they're following the absorbance over time. So first off, they start with 0.1 B and 0.1 C. And they follow that over time. And then they're going to run it again, and they're going to double their amount of C. So notice they have 0.2 for their C this time, and 0.1 for their B. And they follow that over time, the absorbance as it changes over time. And then they go back to having 0.1 C, but this time they double their B. So they have 0.2 of B, and again they follow that over time. So they're trying to see how does the initial amount of B and C affect our rate. And the way that they're measuring it this time is by the color, green, C is green. So as the reaction goes, the absorbance goes down because C is being used up. Making sense? So C is a reactant, it's green. Notice when we have more C, we have more absorbance to start out with. And then it always goes down over time because green is our reactant and our products are colorless. They want us to use this information to find the rate law and the rate constant. So we know that rate equals K, and then we have our reactant B raised to some order, which we don't know yet, and our reactant C raised to some order, which we also don't know yet. So our goal is to use this data that they've given us to figure out the orders for B and C. All right, remember that rate has to do with the change in concentration over time. So I need to be able to use this data that they gave me to figure out how the concentration changed over time. But the data that they gave me was for this absorbance, not the concentration. So I need to figure out what the concentration is. And to do that, I need to figure out what the value is for little a, for this colored reactant. So I'm going to use this equation, absorptivity equals little a, B times C. Now they already told me that B was 1 centimeter. And I need to find an A value and a C value so I can find little a. Now we're talking about the colored reactant only. Spectroscopy only works with colored reactants. All right, so let's talk about how to find little a. We're going to rearrange to find little a, absorbance over B times C. And we're talking about the concentration, when we say C, of our colored reactant. So we're going to use a data point where our concentration is known. And our concentration was only known at the beginning, right? So at the beginning of experiment 2 is where we're pulling this data from. You can pull this from any experiment, but at the beginning of experiment 2, we know that our molarity for C, that's the colored reactant, was 0.2. That's our concentration. And then we know that the absorbance at the beginning of experiment 2 was 1. And we know our path length is 1. We could also use the information from the beginning of experiment 1. And at that point, our absorbance was 0.5, if you look at that graph. And our concentration for C was 0.1. And then our path length would have still been 1 centimeter. All right? So we can calculate our little a value there. And we find that it's 5 and then 1 over molarity times centimeters, or molarity to the negative 1, centimeters to the negative 1. Absorbance has no unit. This 1 up here. All right, so that's our little a value, and that is going to allow us to convert all these absorbances into concentrations, because that's really what we care about when we're talking about rate. We care about the concentration, not the absorbance. But the absorbance will allow us to find the concentration. All right, so now let's use that to find the initial rate for each experiment. Initial rate for each experiment. So if we look at experiment 1, the concentration in experiment 1 is equal to your absorbance divided by A, which we just found to be 5, times your path length B, which we know to be 1 centimeter. And they're saying that the absorbance here is 0.375. Okay, let's see where they're pulling that from. They're getting that 0.375 from right in here. I'm guessing right here at 60 seconds. Okay, we're trying to find the initial rate. So we want to know how much did it change in this initial time block. So in this first 60 seconds, our absorbance went from 0.5, which we already know the concentration was 1 right there. The absorbance went down to 0.375. And so we're trying to find what the concentration was at that point. So at 0.375, our concentration was 0.075, as calculated using C equals absorbance over AB, so 0.075. Our concentration started out at 0.1, right? So our rate is equal to our change in concentration over time. So in that 60 seconds, our concentration changed by whatever the difference is between those two, and then we divide by our time. So this was our rate, molarity per second, for experiment 1. All right, we'll do the same thing for experiment 2. This was our absorbance at 60 seconds for experiment 2. So we can use that to find the concentration at 60 seconds. We know that in experiment 2, we started out at 0.2 for C, right? We're only talking about C here because that's our only thing that we can follow because that's our colored species. All right, so it changed by 0.05, and we're dividing by 60 seconds because that's our initial time block, and there's our rate. And then we'll find our rate for experiment 3 the same way. This is our absorbance at 60 seconds, 0.25. We can use that to find the concentration at 60 seconds, 0.05. We'll find our change in concentration. They gave us the initial concentration as 0.1 for C in experiment 3, and then there's our rate for experiment 3. So let's back up. We figured out little a in step 1. We're using that along with our absorbance at 60 seconds to find our concentration at 60 seconds. Then we're saying, okay, how much did that concentration change? Let's divide that by the time, and there is our rate. And we're looking for the rate at the beginning, because remember the rate changes as the reaction goes. So we want to know just what was the rate in that first time block. So now we have our rate for experiment 1, experiment 2, and experiment 3. Now let's compare that to how our concentrations changed. So here we have a chart. We have our initial concentration from B and C for all 3 trials. They gave us this information. And then we have our rates that we just figured out. Okay, and we're trying to figure out the rate law. So let's look. In experiment 1 and 2, what did they change? They changed the concentration of C. And what did they do to it? They doubled it, right? And we want to know, what did that do to the rate? Did it have no effect? 0 order. Did it have the same effect or a direct effect? First order. Or did it have a squared effect? Second order. So if our concentration was multiplied by 2, was our rate multiplied by 2, or was our rate multiplied by 4? So let's look. Our rate did change, so we know it's not 0 order, but our rate was multiplied by 2, which is the same thing as our concentration. So if your rate and your concentration do the same thing, that's a direct effect or a first order effect. All right, now let's figure out what effect B had. What experiment should we look at? We want C to stay the same, so we can talk about B. So let's look at experiments 1 and 3, because in 1 and 3, C stays constant. So from 1 to 3, what does B do? What did they do to B from 1 to 3? They doubled it, right? And let's look at what that does to the rate. So we're looking at 1 and 3. We're not looking at 2 here. 1 to 3, what happened to the rate? So B was doubled. Did that have no effect on the rate, a direct effect on the rate, or a squared effect? Well, B was doubled, and so was the rate. So the same thing happened to B and the rate. So that also makes B first order. All right, so see what we're doing here? We're using table logic to say, okay, this doubled, this also doubled, first order. This doubled, this also doubled, first order. So I can say that they are both first order. I'm going to show you the math of that. You can compare experiment 3 to experiment 1, because in those two, we have something that's staying constant. So we set that up. Our C's cancel if we're doing 1 and 3. And that allows us to find that B is first order. When we divide our rates, we get 2. And we get 2 for our concentration. So 2 to the first power is 2. We can use experiments 1 and 2 the same way. In those, our B values cancel. So we have 2 raised to what power equals 2. So it's also first order there. So there's the math if you want to go back and pause and look more closely at that. So the rate law, would be K equals B to the first, C to the first. And you don't have to write the ones if those are your exponents. So rate equals K, B to the first power, C to the first power. Now if we want to find the rate constant K, we would use any experiment, 1, 2, or 3 that we would like, and just plug in our values. K is going to equal your rate divided by your concentration of B and C raised to their order, and they're both first order. So we pull data from any of those experiments that we would like, and then let's look at our units as we go. We have molarity times molarity, so that's going to be molarity squared on the bottom. So one of those will cancel with that molarity. So we'll have molarity to the first on the bottom and seconds on the bottom. And then we do the math. We get 0.042 molarity to the -1, seconds to the -1, which is also 1 over molarity times seconds, if you'd rather write it that way. If they ask us for the overall order, that's first order for B, first order for C, so our overall order is 2. Right? So that is how we find the rate law and the rate constant if we're given different experiments and we know the initial concentration in those experiments. And we can find that initial concentration using spectroscopy.